Hi YouTube. I know I said I'm going to post this video much sooner than I did, and I'm not a constant content creator. I was actually at that time busy submitting my master's thesis, and there was a lot of editing that needed to be done. Technically it was brilliant, but I'm a terrible writer, so I had to do a lot of work there, reviewing and checking and fixing bullet points and stuff. I decided tonight, well, if I'm going to worry about writing a script for this video and trying to figure out when I'm going to make a joke where it's never going to happen. So I just have the control systems report in front of me, and I'm going to read the headings of the control system report, and that's just going to be the structure of the video, because otherwise I'll never get this out. So this is the control system for the Sentinel turret. We'll start with the control system layout, the control system requirements, then the control loop, what system model we'll use, PID, PI, lead lag compensator. I'll talk about them in a bit, but it's going to be a PID controller. The state space model, so the mathematical model, so that we can tune the control system before we actually code it. Then in MATLAB. Then initial parameter tuning. Then we're going to talk about the sample rate, the closed loop step response, the Bode plot of how the thing is going to respond, to make sure that we fit the design requirements that we talked about. You know, that with this mathematical model that takes into account the weight of the gun and the power of the motors and stuff like that. If we look at the Bode plot, I'm not going to explain right now what that is, but you'll see whether it's going to respond at the right frequency that we need, because it goes into this dip, and we'll explain it later. Then we're going to talk about the UART communication, microcontroller, what microcontroller we're going to use, how to choose the right microcontroller to make sure you don't, use a Pentium 56 core AMD something when you only need like a Arduino. But maybe if you use an Arduino, then it won't be able to do the job. It can't think that fast. So we do some calculations, some rough calculations on how many operations we think it has to do per second, and then you can choose a processor that sort of matches that or exceeds it a bit. So yeah, let's start with, so the lit review for this is just how I chose what feedback mechanism I'm going to use, and that's any way for the system to get back information on the position of the axes. So it can't just blindly position it somewhere. It's not a stepper motor, right? So it has to know where it is currently to know how much power to apply in that process step, so it can position it correctly. So you can have a potentiometer, which is just a resistor. So more resistance means more left or more right. Less resistance means less left or less right. And then you digitize the resistor input through a digital to analog converter, which most microcontrollers have, and then you estimate its value. So the downside of using a resistor is it's not very linear. By linear, I'll explain in a diagram on this side. I mean that for every unit of resistance there is a exact equivalent unit of turn. Unit of turn. You get units of distance, right? So you can get units of turns. So it means that because the track on the resistor might vary slightly in width, along with due to processing deviations or whatever, even temperature. If the temperature is hotter or colder, it's going to change where you think the thing is. So that means you can mitigate this by in your programming code, not just assuming it's linear, but taking sample points and then sort of mapping out the resistance to the correct position, and then you get a more accurate result. But it doesn't matter. We have a much better way of doing that if you're going to use digital systems, which is the encoder. Then you get two types of encoders, basically: a absolute positional encoder and a incremental encoder. So the absolute positional encoder works with gray code. It's basically take a circle, divide it in half, make the one side black, make the other side white. If you shine a laser and the circle turns, it'll either be black or white, right? So you know it's either in this 180 of the circle or that 180 of the circle. Then you make another circle, a smaller circle inside that, and you divide that up into 4 parts. And you go black, white, black, white. So now if you look on the outside one and it's black, then you have two choices on the inner one, black or white. Then suddenly you have reduced your resolution to 25 degrees. So you keep on making more circles down where you divide it alternately between black and white, and it's sort of it's almost like following a binary tree down to where you are, but they're very expensive and you can't do more than one rotation with them. So in other words, you only have 360 degrees, and if you want really fine resolution like we want for 0.02 degrees, you're going to have a lot of concentric circles and they become really expensive. So the other option, the nice thing about these are that as soon as it starts up, it knows exactly where it is because all the little segments coincide with that position. But much cheaper, better option for this is the incremental encoder. So all it is this cartwheel of black and white stripes, and then you have two lasers, and basically it just counts how much it's turned. So when you switch it on, it doesn't know where it is, but as the lines move past the lasers, then it knows if it's turned left or right, and how many steps it has taken. The nice thing about this is that we can turn it around as many times as we want. So we can actually gear the encoder down so that we can take very small amount of turn on the turret side, and the encoder just spins a lot, which gives us very high resolution. So control system layout, I'll show another diagram over here. We'll have so we cut the system off on the cable that comes from the computer. Anything from the computer, that's the tracking and targeting system. So anything that comes out of the cable, that's our control system. So on the one side you have the commands coming in to the microcontroller. The microcontroller sends drive signals to the motor driver. The motor driver takes this drive signal and amplifies it to a mechanical electrical current that the motor will be driven at. Then the drive mechanism will be able to feed back position information using the encoder and limit switches. The limit switches are to stop the thing from moving off the edge if it goes too fast or too far, and also for it to zero itself. So like I said, the encoder doesn't know where it is as soon as you start it up. You'll see a lot of 3D printers do that as well. You know, they go zzz, zzz, and then it sort of knows, okay, now I'm at 0, 0. So after discussing what kind of hardware we're going to have the control system use, let's just quickly talk about the requirements again. So as we said in previous videos, the control system has to be able to operate the turret at least a 4 Hz frequencies, because that's our frequency limit that the human's going to run at. So it has to be able to respond at least 4 Hz. So in other words, make corrections faster than 4 times a second, and be able to control the position and make decisions based on that speed. Then we need to be sub 0.157 degrees in accuracy. So in other words, when the turret's aiming, the control system should be able to control the position of the motor to within 0.157 degrees at the turret's output. So I say at the turret's output because we're going to actually gear down the turret, so the motor is going to be spinning a lot more than the turret is. So on the motor side, it's going to control the motor at like 42 times that, so it has to only control the motor at, I don't think, 20 degrees or something. But it doesn't matter, since we're going to read from the encoder output. It has to be able to stop the turret from minus 35 to 35, so that's going to be done with the limit switches. Then to design the full control system, you have to make a mathematical model of it, and for that you need some properties from the motor, the gear ratio, little things like the expected viscous friction, torsional rigidity of the system. So that all comes from the mechanical system that we discussed. So you work out the torsional rigidity, which means how much does the system flex, because if you quickly torque the motor on this side, then how long is it going to take for the turret to respond on the other side, and that's all going to influence the control system. So then you can build this mathematical model it's called a state space model if you put it in matrix form like this. And this is some advanced engineering math which I'm not going to explain here, but there's a lot of tutorials on YouTube of how to design, go from a system differential equation model to a state space model that you can then apply a controller model to and see what the output is. And it's nighttime, so I have to take this in steps, so you're going to see the daylight and the mood changing several times throughout this video. So we have several controller models to choose from. We have old school ones like mainly used for single input, single output control systems, such as the lead lag compensator and the famous PID controller, and they were all still used when you did a lot of calculations by hand. But there's new control methods that are made possible by our digital processing capabilities. Let me just take these off. Such as the state space controllers. And we've said that our turret is a single input, single output system with orthogonal axes, so PID would be completely fine for us since we're essentially building a servo mechanism. But let me just explain why state space controllers are such a beautiful thing. Since you can model your system mathematically, and you can have this mathematical equation that describes your system, and your digital computers can solve equations, your system is essentially represented by its state. So in other words, what is the value of all its variables? So whether it's a energy storage variable or a position variable, your system is in a certain state. That's what's called a state space model. And if you want it to be in a specific state, so in other words, you want to have the turret's position here, essentially what you can do is you can solve for that state using your system equation like you would a high school solving for X math equation, if that equation realized what a weebit was and was taking protein and pumping for gains, if the gains were extra dimensions. But anyway, there are a lot of things that can be modeled as part of the system using a state space controller, such as the effect that temperature has on your bearings, the change in weight from the paintball hopper, and a lot of the other small nonlinearities that you can model into the system so that you can get a really smart controller that knows exactly how much torque to apply in every situation. But we're not docking with the space station, so we're just going to use a PID. So you build the Simulink model in MATLAB using the state space model, and you plug in a PID controller, then you start tuning it till you get to the steady state error you want. You want to have it have as little overshoot as possible, but being able to get to its target position in time. And then after I had the tuned values, I can start coding the controller for the on the microcontroller based on the algorithm I developed on MATLAB. So you want to balance your control requirements with the cost of the microcontroller. And these days, you know, a microcontroller really costs nothing, and you can even run it on something pretty strong like a Raspberry Pi, and it won't cost you much more than you would have if you chose a some AMD microcontroller. So after you figure out what your control loop is going to look like, you count the lines of code and you figure out how many operations it's going to do. So if it's an addition operation, you count 3 processor cycles, or 4 processor cycles if you're going to be conservative, depending on the microprocessor actually. So check how many cycles it takes to do an operation. If it's to multiply or it's divide, if it doesn't have a divider, how does it do division? Maybe it takes a lot more cycles to do division. And then you can calculate how many processor cycles you're going to require to run through one control loop for the control system. And also you need to take into account interrupts. So if the encoder is going to feed information to you on the lines it's reading, and a limit switch is going to feed you information, these are all done with interrupts. So the program's running through its normal sequence of code, then there's an interrupt, it stops by that line, it handles the interrupt, and it goes back to that code again. So you need to ensure that if that encoder is spinning at its max rate, in other words the turret is flying across, and your processor is being hit with interrupts the whole time, will you saturate the processor with the interrupts so it can't even calculate the next control signal? So an interrupt would also take about 3 processor cycles to initiate, and then how many other processor cycles you need to run through the interrupt cycle. So if you're going to code it, don't code the interrupt to do addition, just raise a flag and then put the addition code in your normal control loop, so that you know you'll always run through the control process, then add whatever the encoder told you to add, and then you can do the loop. It's just to stop. You want as little code as possible in your interrupt sequences so that you don't saturate the processor and don't get back to your control loop. So in my case, the encoder had a maximum output of about 20,000 interrupts per second, and adding that all to a table, we can see that that's about 80,000 interrupts because it's a quadrature encoder. Then expected clock cycles per interrupt is 6 because I only did a quick comparison to see which way it should add or subtract from the current position count. And then you calculate the total millions of interrupts per second that the processor has to handle, and also the calculations per second. And then it came down to 2.19 million calculations per second that this control system will have to do at maximum rate. And then I could choose a microcontroller based on that. What I went with is the RL78, which is a very obscure microcontroller that we were taught to program in at university, and it's super powerful. It has 44 million interrupts per second that it can handle. It was kind of a pain to work with. The documentation really taught you how to read microcontroller manuals. It was, I would say at the time it was a nightmare, but it really taught us a lot about the internal workings of microcontroller. It's made by Renesas, but I wouldn't recommend using the RL78 for a project again. There's so much better microprocessor out there. I mean, look at the ESP32 Wi-Fi board. You can then send all the signals over Wi-Fi, and it's definitely powerful enough. It's got 2 cores. Renesas RL78 only has 1 core. This is a pin out diagram, so you then want to figure out which pins of the microcontroller can do which things. So a MCU has dedicated circuits for certain things, so you don't sometimes even need to write code to read an encoder. You can literally just hook up the right pins, and then they have some built-in circuitry that outputs the number of counts of the controller for you. So do your pin out of the control system, which pins can handle limit switches, which pins can do USB UART communication, which pins can do PWM output for your motor, and then you can start mapping the pins to your controller code and build up your processor code like that. So this is just a pinout diagram of my of the Sentinel turret. So then you have to choose a motor driver, so you know how much current your motor is going to pull because you chose the motor, and you know what kind of torque it has to output, and therefore you can equate what the motor current pull should be, and you can then choose the right motor driver that will receive a PWM signal from the microcontroller, and the transistors in it will convert that into a much stronger current for the motor to be driven at. I chose a Cytron MDD 10 amp motor driver. Cytron it's a brilliant company. I really recommend you guys use them. It's not sponsored by them, like I haven't contacted them for over 3 years, but their driver boards are very high quality and very cheap compared to other brands that I've considered. So in conclusion, you have the 12 volt supply that goes to your controller board and your motor driver. You have the encoder signals that go to these pins. You have the USB for commands for input, and then the PWM signal that goes out from the controller to the motor driver board. The motor driver board converts this into a current that drives the motors, and the motors give feedback through the encoder signals again.